MorpheusChair, the program where you learn how to build robots like these from your comfy chairs. So in this program, we're going to create the following line program for this little bad boy. So for that, we're going to use simulation. And you say, hey, but Mike, I have the real robot. Why do I need a simulation? Very good question, anonymous person. Simulations are used in robotics all the time for various reasons, but for our intended purposes, we need a simulation to be able to iterate and generate the line following algorithm the faster we can. If we have a simulation, we can test our different versions of the program, and we won't have to deal with that the motors don't work properly, or that we have to connect through SSH and download the code and all that stuff. And then when we have the good line following algorithm, we will test it on the robot, and then we will concentrate on solving only the problems related to the real robot. But the problems related to line following will be already solved because we will have solved it in the simulated phase. So without further ado, to the computer. Okay, so the first step for this is we have to adapt our simulation in a way that it is similar to the floor that we will use in the follow line in the real robot. So what we are going to do is create a model with a photograph of the floor as a texture, and that's it, and we will add that to the simulation. So the first thing is we're going to open Blender, and we're going to add a plane. So that plane, we will give it some dimensions. Let's say, I don't know, like 10 meters by 10 meters, for example. It's good enough. And now what we're going to do is we're going to add a new material. Yeah, and we will say base, for example. We add the texture, we'll get the image. That's basically a photograph of my floor. There you go. So that's the photograph of the texture of my floor, basically. So now we unwrap the mesh, which is a plane. And that way we can choose how it will be seen in that plane. So you can play around. For example, we can scale it up. That way it will repeat. We can also zoom in if we want, but we will leave it like that. It's basically, we respect the colors and the different textures that you get there, more or less. And that's quite it. So once we have it, so now we're going to add the lines. So for that, we're going to use simple planes that we will texture with a white material, which is the color that's our tape. So what we are going to do is scale the plane to be around 3 centimeters of width, which is the width of my tape. So there we go, 3 centimeters more or less. And now what we're going to do is duplicate the lines, and we can move it, and we will do like a simple path that the robot can follow. There you go, nice and cozy. Yeah, I think this is more than enough to test it. So now once we have this all, we have to export this to a DAI file. So we just select everything and then we hit File, Export, and we export it as a die. And that's quite it. So the first thing is we're going to launch our Morpheus Sim project. You can launch it in your local computer. Okay, then when the project is loaded, what we're going to do is, first thing is update any changes that there might have been in my repository. So okay, there you go. Once we have it, we will open the IDE and see what we can do. Okay, so I'll show you how I've done the model. So first things first, what we have is our beloved MorpheusChair package. So if we go here, you have models, and inside it we have generated a folder which is called line test, and inside it we have the meshes that we generated through Blender, and then we have a config and a SDF file where we specify the name, line test of the model, specifications, who made it, and so on, and then the SDF, which essentially what it is a static element that has a collision and a visual. A collision, which is a plane of these dimensions, 10 by 10, and has a really high friction. And then the visual, here we state the die model that we exported through Blender. Okay, so in this case we're going to select this new test floor full. Okay, fair enough. So now what we're going to do is we are going to say that the world that we're loading, which is this one, has this model, which is line test. Great. And we just place the lights, some sun, and that's it. So we are going to launch the real robots, the MorpheusChair Sim, yeah, which essentially loads this world and spawns the Morpheus robot. Yeah, so let's do it. So we go here, we launch it, and we go here and launch. So as you can see, it's the model that we generated, just a little bit more complex, but essentially it's the 4 lines that we place here, plus this one, plus this triangle there. Okay. Another thing that we have to check is that the camera can see the lines, because sometimes if we export it wrong, then we might see it in the simulation, in the visualizer, but then when we render it through the camera plugins, we won't be able to see it. So we will launch this RQT image, and if you're in a local computer, it will pop up a GUI. If you're in ROS Development Studio, you just have to go to Graphical Tools, and all the things that pop up should pop up here. There we go. So now we select the one that we want. In this case, we want this one. And there you go. So let's have a look. If we move the robot around, just like that, fast and dirty. There you go. So we can see perfectly the lines. Fantastic. So there we have it. So now we have our model of our floor with the lines ready to go. Okay, we left it here. So now what we're going to see is how to generate this line following program. So let's have a look. So we go to the IDE and we go to the MorpheusChair scripts, and I left in the video description, as always, the Git where you can download everything we're talking about here. So we go to line follower, and line follower is basically a class that takes a few arguments that we're going to see how we use it here in the main function. So the main function, what it does is we initialize a node, we state what color we want to follow, and this is really important. This is really important, because depending on the color of your tape, then you have to change the RGB code that you have here. Okay, so how do we get the color here? Well, the best way to do it is just through a plugin or a program to get colors of an image. So for example, I have this plugin, which is the color picker, and what it does is every color that it sees in the web page, it just gets that color. So if you go to the repository and you go to test images, you can test this image, for example, that we have here of the simulation, and we say, hey, which color is it? And we go here and you say, okay, it's 255 in RGB. Perfect. If it was another color, then we would get the code that we need. We state it here, and then we initialize the line follower that needs the RGB to track the color error percentage, so which percentage above and below we accept, and then the color calibration is just to get those images in the simulation through the GUI in a way that it doesn't do anything, it just spits out the images of the camera, and you can get a screenshot of that. So let's have a look. And then once we have it, then we loop, and we stay there forever and ever. So let's have a look how the line follower works. We won't go into much detail. If you have any questions about certain topics or certain elements here, please leave it in the comments below. So what we do here is we create a subscriber to the camera topic, which is Morpheus Raspberry Pi node image raw, which is the same one as in the simulation and in the real robot. It's good that your simulations are exactly the same as the real robot to make things easier. And then we do a publisher into the command vel topic, which is by default Morpheus bot command vel. Again, it's the same in the real robot and in the simulation, and we will use this one to move the robot around based on what's the detection of the line. So we have this camera callback, which is called each time that we receive an image in the topic, and what it does is process the image received like that. So data is the image received, and what we're doing is using this bridge object. So CV bridge is essentially a module, a method, a class that allows us to convert from ROS images to OpenCV image format, and with that we can use all this OpenCV library, and it's really powerful. So what we do is we get it with the encoding BGR8, and we get the image. Okay, now we have the image of the camera, the one that we just saw here. Yeah, exactly the same. So now what we want to do is resize it. Why? Because working with smaller images makes you go faster, and we don't need a lot of detail here. We just we need only to know if it's white or not. So we don't need a lot of very big images. And what we do is we reduce it to the 20%. So we are making them really tiny. That way it's easier to work with. And it's a common practice. We use this method in AI, we use it in everywhere. So once we have it, then we get the shape of the image. So height and width. And this will be used as reference afterwards to know where the center of the detection is and if we have to turn right or turn left. So we do some gibberish here. It's not important. Again, if you have any questions, please leave it in the comments below. And this is important because what we do is we convert the image into HSV, which is more stable versus lighting conditions. So if we change lighting conditions, it doesn't affect that much to HSV. And then when we do is we generate a maximum and minimum value of the color in HSV format that we want to track. This means that this is the range of the colors that we want. Yeah? And then we do a mask, which what we do is essentially all the colors that are inside this margin, this range, we consider them let's say white, and the other ones we consider them black. And once we have it, then we can combine it with the original image. Okay. Then what we do is detect the contours. And from there, we extract the centroids, which basically are blobs of colors, and we generate where we think the most quantity of white is, if there is one blob or various blobs. Again, it's a very deep subject, but basically here we're detecting where the line is. Yeah. Okay. Once we have it, then we draw a circle of a certain color, red, into the centroid that we think it's correct. Yeah. And that way we now have this centroids detected, which is a list if we have various centroids, and what we will do is select the one that it's closer to the robot. That's more or less it. Once we have it, then we basically have a center, a position in X and Y in the image, and the height and width of the image. And based on that, we will move the robot. So let's have a look on how we do this very fast. So essentially what we check is that we have like a point centroid. If we don't, then what we do is we will make the robot move in a spiral trajectory so that it tries to search for a line. If we have, then what we do is do the difference between the origin, so let's say the center of the image, so here basically, and where our blob is in the X value, let's say. So how much to the right or how much to the left is it from the center? And then in the case of the Y, we are only interested in the height. So it really doesn't matter how how high it is versus the center. It's just how high it is. So we want to know if it's very far away from the robot or very close to the robot. It's essentially that. Once we have it, then we calculate the angular and linear velocities. The linear velocity first. So as you can see, we give it a base speed, and then we subtract the delta 1, which is basically the value of the centroid. This means that if it's very close, so the y, it's this value. This means that if we're here, y is 0. If we're here, y, it's the maximum height. This means that if the image, if the blob, the centroid, is around here, this means that it's really close. So the value of the y, it's high. If it's here, it's far away. And it also means that the y, it has a value, a lower value. Yep. So higher values means closer. This means that you have to go slower, otherwise you will lose the line. Yep. And the other way around, if it's further, you want to subtract less speed because we want to go faster. Yeah. And this factor is just to compensate the values of delta so that we subtract a reasonable amount from the base velocity. And then we have the angular, which this is more intuitive because what we have is the value of delta, which is the difference between the center and the blob. This means that if we have the blob with higher values of x, which is here, higher, x is here, lower is here. So if we have higher values, so a value positive, which means bigger than the center to the right, then it means that we have to turn to the right. So this means that if we go here, this is positive, and we have to turn to the right. So positive means to the right, and to the right means a negative turn. That's why it's changing the sign. On the other way around, if we have the robot to the left, then the delta is negative, and therefore it makes the robot turn with an angular velocity of positive, so it will turn left. Yeah. When we execute the program, and you'll see it much faster. Yeah. So let's execute it. So I'm going to kill this and do simulation, source level setup bash, ROS back profile, and ROS launch Morpheus, ROS launch Morpheus line follower launch. Okay, so you can see here the centroid values, and we can see here the detections, and we also can see that the robot is following. So let's put it like that. There you go. And here we can put it like this. There we go. So now what we see is that it's detecting the line here, which is quite reasonable, and now it will detect the blob of the line to the right. This means that, as you can see, the speed is negative, because that means a turn to the right. Yeah, and there you go. So it's following the line. Fantastic. As you can see, the speed is quite low, and the reason is because if it goes too fast, you have to have a better control of this. and you have to predict the trajectory. If you go this slow, it's not necessary to generate the trajectory and a path so that you can know in advance which speed and turn you're going to do. You're just doing it on the fly. So it's slow but steady. Here, for example, there's an interesting case because now you may detect a blob here, two blobs, because there's a separation. So let's have a look what happens. There you go. You see that it detects two blobs. So now because the way we detected and we filtered, it got the first blob. This goes to this part here. We are trying to get the value of y the lower possible, and lower means further. So we give priority to blobs detected further. That way we don't get concentrated on the line here, but on the one that it's a bit more further. And now what we're going to see is the behavior when it loses the line. And as I said, all this, we have tested it in simulation, so you can do as many tests as you want. There's no problems of connecting, there's no problems of batteries and engines and motors working the way they shouldn't. You just concentrate on perfecting this algorithm. That's why this algorithm works more or less okay, because I could iterate over it and over again. Okay, so we're going to lose the blob. There you go. So now it starts with this searching pattern again. As you can see, it's speed 0.05 and a turn of 0.2. So basically it goes a bit in linear and then turns. You can see that it got the line again. There you go. This is the tricky part, but because we make it go slower when the line gets closer, it allows it to get it again. And there you have it. So you have a line follower that can follow the line endlessly. And we can do different tests. For example, let's try that one. So we are just going to reset the simulation. Okay, and now we can move it to here, for example. There we go. And we turn it like that. There we go. And now we execute the program and see what happens. There you go. So it got the line super fast. And there. So now what it's doing, and we might get the centroid here. So let's have a look. And all these tests, we will do it also in the real robot, but doing this we can see if it works or not and how it should behave in the real robot. So there we go. So it's, as you can see, it's detecting more or less this blob and sometimes that blob. So that's something that we could optimize. But it seems to work quite well. Also, to optimize, of course, prints in your program, it's not very efficient, especially in Raspberry Pi, which has limited resources. So we will remove the prints once the testing is done in simulation. Again, in simulation you don't have resource problems. So again, you just concentrate and make things work. And yeah, I think that's it. We're back. That's all for today. So in the next video, we are going to create a support for the camera. We will generate it through an online free CAD software, and we will generate the 3D models that then we will use to 3D print a support to have the camera in a correct mount and not in this dodgy system. If you want to see that video, smash that like button. Until then, keep building. Keep building.